Hey guys, as you know, I'm trying to solve the physics of the huge rope swing in Moab, Utah. I approximated that 12.14 meters of the rope is anchored to the top of the structure. My mass of the person is 100 kilograms. The static elongation of the rope that they used, I'm saying, is 3.5%, which means that the rope stretched 3.5% of its original length when an 80 kilogram weight is hung from it. Using that length, I calculated the spring stiffness of the rope, which is 788 newtons per meter. So I wanted to calculate the final, the speed at the bottom of the swing. So here's my initial state. This is an ideal rope. So at the initial state, the rope is 36.58 meters, and the final state, the rope is still 36.58 meters. Here, I used the energy principle to calculate the velocity. I set work equals 0, set my final kinetic and potential energies to equal to the initial kinetic and potential energies. The kinetic energy of the ball initially is going to be 0 because he is up here at the top and not moving. So I solved for V final, and I got 26.78 meters per second. Then I found the tension in the rope at the bottom of the swing. I used the perpendicular force equals tension force minus force of gravity. Then I solved for the tension force. After plugging in my numbers, I got that the tension in the rope at the bottom of the swing is 2,940.5 newtons. Then I had to calculate the speed at 30 degrees from the bottom. So I had to find height final. I calculated that to be 11 meters. Then I used the energy principle again, using the same things that I used last time, except here kinetic energy actually has a value. And I solved for V and got 26.08 meters per second. Then I found the tension in the rope at 30 degrees to the vertical. I used the same formula as the previous problem, force tension equals force perpendicular plus force of gravity, except for the force of gravity I used the perpendicular component of gravity, so I multiplied by cosine of theta, which would be cosine of 30 degrees. Then, after plugging in my numbers, I got that the tension in the rope at 30 degrees to the vertical is 2,708.1 newtons. Then we had to calculate the stretch, or estimate the stretch of the rope at the bottom of the swing. This was one of the formulas I had. F tension equals F perpendicular plus mg, which is the force of gravity. That's the equation there. And then I also used the energy principle to get this here. So in both of these formulas, I had two unknowns. I had the stretch of the spring is unknown, and I had the final velocity as unknown. So I used velocity squared as a common variable and set the two equations equal to each other. Once I got the stretch, put it to one side, I got 4.45 meters for the stretch of the rope at the bottom. Now, at 30 degrees, I used the same formula as I did there, except I plugged in for the force of gravity, mg cosine theta. Doing that same process, I got the stretch of the rope at 30-degree angle from the trajectory of the bottom as 4.3 meters. So now I'm going to model the swing in VPython. Here we go. Here, the red arrow is velocity, the yellow arrow is tension force, the green arrow is the parallel net force, and the blue arrow is the perpendicular net force. At the bottom, the tension force and the velocity arrows are their biggest, so that means that those values are greatest at the bottom of the swing. Now I'm going to show the model of an ideal rope. So it has a higher spring constant because it doesn't stretch. So as you can see, it's much higher off the ground. The motion is more semicircle-ish than in the actual rope. My computational model and pen and paper analysis supported each other. So I hope this video helped you guys understand the physics of the rope swing better.